Welcome back to Multigrid Methods. Today we're in Chapter 4. We completed a discussion about the approximation property already. We talked about Richardson smoother, and now we're getting into the second key component for the sort of generic or abstract energy norm convergence of the two-grid method. The first property was the approximation property. The second one is this smoothing property, which we're kind of in the middle of today. Last time, I think we ended with this little lemma or around there. I made a claim about this function f of x equals x times 1 minus x to the 2m power. And I said this function in the interval 0 to 1 is a convex function. That's not true. So I want to clarify that. So the result is still correct, but the function looks something like this. For larger and larger m, basically that curve becomes flatter and flatter. There's a 0 here at x equals 1. And of course, there's a 0 at x equals 0. This maximum point here is what we're going to call x0. So proving that this is a maximum point over the interval 0 to 1, point where the function reaches its maximum, is a little more complicated than what I said. You're still going to use the derivative test to find that to find the value of this x naught. Now this point here also has a derivative of 0. We're going to reject that one, the point at x equals 1. So the reason why we're going to take this value of x0, which is strictly between 0 and 1, is because that's the true maximum point. This turns out to be a point of minimum. I think the function goes off like that. It may, I forget what it does. I think maybe it always goes off like that, but it may also go down. I forget. But in any case, let's see, it's an odd function. Yeah, so it always goes up like that. In any case, you can show that this point x naught is always going to be a maximum of this function on this interval. But it's not because of the claim that I made last time that the function is actually convex on the interval. It's a little more complicated than that. You just have to show that it's a relative maximum. In other words, the function is decreasing if I go this way and is decreasing if I go that way. The problem is it does start to increase if I go beyond that. But the result is still the same. It's just a claim I made was not quite correct. So I added a little bit in the discussion to address that. Now, the next result that we wanted to prove, I don't think we got to this result yet. Is that correct? Or did we do, can anyone say, did we do this smoothing property theorem?
Don't
Or did
think
I just,
so.
okay, that's what I was recall as well. I think I just got to the statement of it, but now we want to actually prove it. And I did realize that there was an assumption in here that was not necessary. I think before, if I'm not mistaken, I was previously assuming that A0 satisfied the Glerkin condition. We don't need that because this is smoothing, and smoothing really only pays attention to what's happening on the current fine level. And the fine level here is the 1 level. So we don't need the thing that I claimed earlier. So we're going to apply Richardson smoothing, which is, by the way, just damp Jacobi method with omega equals to a half. And choosing omega equals to a half, let me remind you, the eigenvalue curve looks like this. It basically touches down to exactly 0 here at k equals n plus 1. So this was different than what we called the optimal smoothing for the Jacobi weighted Jacobi case. The curve was a little bit different. In fact, the curve that we got for the optimal Jacobi smoothing was obtained for omega equals omega naught, which was 2/3. This one here is when omega is taken to be a half. And what we're finding with this so-called Richardson smoother is that we have a curve which has or sees the eigenvalues for all of the frequencies in the high frequency range, which is this range, being less than 1/2 in absolute value. And of course, in total value, they're less than a half because these are all positive. So the curve is right here. If we choose omega equals a half, we're always less than 1/2 in value. So that was slightly different than what we had previously with the weighted Jacobi smoother with the optimal parameter. So that's why I'm emphasizing. Now it is just damped Jacobi or weighted Jacobi, but it's with omega equals a half. So it's different than it was before, than what we assumed in chapter 3. There is some constant C2 such that the norm, this is the error matrix for smoothing, error transfer matrix. The reason why we're raising it to the M1 power is because we're going to do M1 smoothing operations in our multi-grid algorithm or our two-grid algorithm. Remember, what we're interested in here in this chapter and like last chapter is just what we call the one-sided the one-sided two-grid method. And so that one we chose M1 to be some positive integer constant, and we chose M2 to be 0. I could just make this M. This is not anything special here. This is just some positive constant, um, positive positive number. Now, so K1 again is the error transfer matrix for damped Jacobi. K1 to the M1 prime or M1 is the error transfer matrix if we apply that damped Jacobi method, or in other words, the Richardson's method, M1 times. We're going to measure it in the A1 squared norm, and we'll see why this is important later. We're going to measure it in the A1 squared norm. So this, as I said last time, is kind of like, if you know what I'm talking about, kind of on balance with what we call the Sobolev H2 norm, the Sobolev H2 norm. This is less than a constant C2 times the square root of lambda 1. This capital lambda 1 here was our asymptotic spectral radius. It's a number which is larger than, just a little bit larger than the spectral radius. And of course, the spectral radius is the largest eigenvalue. All right, so this is the largest, or the asymptotic spectral radius for the stiffness matrix. Now, remember that the stiffness matrix is the stiffness matrix that we're always talking about, A1, and it has positive eigenvalues. Okay, so that's that upper bound for that. I think that was, if I'm not mistaken, just to remind us, this was 4 over H1 over M1 times the regular energy norm of this vector V1, where V1 is just some arbitrary vector in Rn1. So this is like, so this we said was like the H2 Sobolev norm. This is like the H1 Sobolev norm and is commonly referred to as the energy norm. Sometimes this is what we call the double energy norm. In particular for our application, because we're talking about the one-dimensional version of the finite element method, we can take, in this case, C2 to be equal to 1/2 square root. Okay, so let's see how this works. The first thing we want to do is figure out, well, what does this norm look like? The norm of this vector K1, that's the error transfer matrix for smoothing because we're doing M1 smoothing steps. Well, by a little identity that we demonstrated maybe 2 classes ago, this A1 appears in the standard Euclidean norm on level 1, the fine level, just by pre-multiplying this vector. So A1 appears here. And of course, we're taking the norm squared, so the squared follows around. This, of course, is now just the Euclidean inner product because we're squaring the Euclidean norm on level 1. So we get that. Right? So remember, that's just the usual sort of thing. The one norm of any vector is equal to square root of the Euclidean norm of that vector against itself in the Euclidean 1, or in the Euclidean inner product on level 1. Hope I said that correctly. I think the symbol's correct, at least. That's where we're getting this. Now let's write V1 in a basis, as we're always doing because we're doing Fourier analysis as our main tool right now, a basis of eigenvectors for the stiffness matrix. Okay, so write V1 in a basis of eigenvectors of the stiffness matrix. That means there exist these constants V1K, and they're uniquely determined constants once we specify what basis we want, such that V1 is equal to this linear combination. All right, so we're going to plug this into here and here. And then we're going to hit that with the K1, M1 matrix, and then follow that up with hitting it with the A1 matrix. Well, we know that the eigenvectors of the stiffness matrix are also eigenvectors of the error transfer matrix and any power of the error transfer matrix. And what happens is when I do those applications, I'm going to get the following. Since I'm doing M1 applications of the error transfer matrix, I get the eigenvalues of the error transfer matrix to the 2M1 power. And I'm going to get the eigenvalues to the 2 power. Okay, each eigenvalue gets squared. And in there, I also have the coordinates in this coordinate representation or this basis representation of V1. So this is a fairly simple little application. This comes because of the normalization of the eigenvectors for the stiffness matrix. So remember we said somewhere along the way that if I take a k eigenvector against an L eigenvector, then I simply get n1 plus 1 over 2 Kronecker delta KL. Just in case you can't see that, let me move it down here. So that's what we call the normalization. So that's where that comes from, and everything else comes from standard applications. All right, so now let me modify this in a kind of straightforward way. What I'm going to do is I'm going to, let's see, I think I may have, okay, right. Now I'm going to split this up in a certain way. So let's see how this works. So I have equality here. I'm not doing any estimation. I just lost my place there for a second, but I think I've recovered now. So we're going to take one of the eigenvalues and move that out front. All right. And that's because that's what's going to appear in the energy inner product, energy norm. So we're going to take one eigenvalue out with V1K squared, right? So that leaves here just a single eigenvalue left. That's that guy. I'm going to divide that by lambda 1. And if I divide that by lambda 1, I'm going to divide each one by lambda 1. I have to also multiply by a single lambda 1 in order to balance that. This is the normalization constant that was out there first. No problem there. And this is by definition what are the eigenvalues for the Richardson's method. Okay, so we showed this last time through a brief calculation back in this section here. These are the eigenvalues for our weighted or damped Jacobi smoother whenever omega is equal to 1/2. That's what we call the Richardson's smoother, right? So that's just a replacement there. Now, this function here, so let's see, I'm going to keep that, no approximations there, no approximations there. And this guy here, what I want to do is I want to observe that that is just my function GM1, okay? And I'm going to take the maximum of that guy, right? So let's take the maximum of these values here. So each one of these values looks like an X. And what do we know about that X? Well, this X value here is between 0 and 1. Okay, it's between 0 and 1. Now, these are discrete values, right? Because the k's here are discrete. So that's the first thing to keep in mind. They're discrete values. If I take the largest of these values, right, and I can call them something different like x, for example, x or xk, because I'm alluding to the fact that xk, if I define it as being this, is some number between 0 and 1, but they're discrete numbers. Let's take the maximum of this function. So the maximum of that function I'm going to call gm1. And notice that it depends on different values of m1, so that's why I'm keeping that as an m1. So that's all I'm doing there is taking the maximum of that. It's a positive number. I can argue that no problem. And I'm going to pull it out front. What's left is, of course, lambda 1, that didn't change. The normalization, that didn't change. And then these guys, that they didn't change. Okay, so I get this. Lambda 1 gm1 times v1 in the a1 norm squared. So this is precisely here. This guy here is just that. And I leave it to you as a very simple exercise to show that. The fact that there's only one eigenvalue or only one power of the eigenvalue is why it's the A1 norm rather than A1 squared norm. The A1 squared norm would have had two powers, or a power 2 of lambda 1k. Now, GM1 precisely is just this function here. I've taken the max over these discrete values, 1 to n1 of these discrete values or these discrete inputs here. I can call that xk if I like. I could have called that xk, I didn't, but xk here is equal to lambda 1k over capital lambda 1. And these guys are less than or equal to 1. In fact, strictly less than 1 and strictly greater than 0. Okay, if I define them that way. So that now calls into mind that lemma that we just proved. The lemma that we just proved said that if you make this into a continuous variable, that's fine because these are discrete values. If I maximize over a larger set, namely the continuum from 0 to 1, then I can show that this is less than some number. All right, so the lemma that we just proved showed that GM, well, my argument just on the last page shows that GM is less than that function because we're maximizing over a larger set. And now that lemma that we just proved in inequality 7 in particular, that is less than, this function is less than 1 over 2 times m. So now we have it because this is just GM. We can fill it in, right? Okay, so GM is less than 1 over 2 to the m, but we have a capital lambda 1 there, and now all we have to do is take square roots on both sides here and here, and we get precisely the result that we wanted. And in particular, we do a little bit better because we do a little bit better than finding just some arbitrary constant here. We know what that constant is. It's got to be square root of 1/2. Okay, so that's what we call the smoothing property. Estimate 8 is called the smoothing property with a constant C2. In particular, I would say with C2 equals to square root of 1/2. Now, here's the whole thing about what we're going to be doing for the rest of the book. In the rest of the book, we're going to be interested in multigrid methods on very complicated meshes. And so remember, let me remind you what we're doing. We're trying to solve this problem. All right. So that one-dimensional Poisson problem. And then later on, we're going to look at more complicated stuff. Like, for example, suppose that we want to solve that same problem or an analog of that problem in higher dimensions. So where this is now our omega. So we might want to solve minus Laplacian of u equals f on omega and u equals 0 on the boundary, right? So later, that's what we're going to be interested in doing. So we're going to be doing that by making a very complicated finite element mesh to solve that problem. Whereas here we're doing something very simple. Our finite element mesh is essentially some sort of uniform, very simple thing. We're going to be able to prove the same sort of results in this more complicated setting. The problem is, or the difficulty is, we won't be able to show it with this C2 constant being so trivial. We might get something which is C2 maybe equal to 2, or maybe we just won't know what it is. It'll depend on the mesh that we have, the actual domain that we have. So lots of things. So right now we're in a very simple setting. Later we're going to be a very complicated setting. Both the approximation property that we talked about and the smoothing property that we talked about, we've developed for this very simple case. Later on, we're going to develop it for the more complicated case. And in those more complicated cases, we won't know what these constants are exactly. But in any case, we still will call that a smoothing property. We'll try to establish that. Well, now we have the two keys that we need to open this door of convergence in the energy norm. So we're aiming to prove the two-grid method is convergent, and we want to show that with these two properties that we just now justified. And again, we've only justified that for this very simple case. We've only justified these properties right now for the very simple case. But that's okay. So I just want to show you how this works. Okay, we have smoothing, we have approximation. Let's turn those keys and open this door of convergence. Suppose that the two-level grid is uniform and nested. So remember what that means. That means in our case that n0 plus 1 is equal to n1 plus 1 over 2. And we're using a uniform grid. Okay? So we can put the fine grid up above. And the fine grid just is a bit finer, right? Now they're covering the same domain, x equals 0 to x equals 1. But just keep in mind, that's what we mean by saying that the two-level grid is uniform and nested. A0 satisfies the Galerkin condition. What does that mean? Well, we know what our prolongation and restriction matrices are, and we have discussed the fact that R0 equals P0 transpose. Now, all I'm saying is A0 must be R0, A1, P0. Okay, so it satisfies the so-called wrap condition. So this is what we mean by saying that A0 satisfies the Galerkin condition. That's that condition right there. Suppose that M2 is equal to 0. I forgot to change this, so this should be corrected to say we're using here smoothing. This is a bit wordy, but I did correct it in the lecture notes. I just forgot to copy that over into the slide. Suppose that M2 is equal to 0. M1 is some positive constant. And we're using a smoother based on the Richardson strategy. In other words, the weighted or damped Jacobi method with omega equals a half. So I'll fix that later. Let me make a note here that that needs to be corrected. As I said, it's corrected in the lecture notes. Then the two-grid method converges. Two-grid method converges provided M1 is sufficiently large. Moreover, we have the following error estimate. The error at step or iteration L plus 1. So this doesn't mean level, this means iteration. And again, I'm using L here for the iteration count because K is going to be my wave number. So the error at iteration L plus 1 in the energy norm, remember this is an energy norm convergence study, is less than C1 times C2. C1 is the constant that came from the approximation property. C2 is the constant that came from the smoothing property. All right, times M1 to the minus 1/2 power. So the minus 1/2 power. So this just means 1 over m1 square root times E1L in the energy norm. In other words, the error at the previous iteration step. So these are iteration steps for the two-grid method. These are applications of the two-grid method. So this means a single application of the two-grid method should reduce the error by this amount, this contraction factor. Now, of course, we want to choose that contraction factor so that it's going to be less than 1. That's what convergence means. It's actually errors going down. If this guy was greater than 1, like 1.5, that means the error is going to be going up and it's not going to be useful to us. What we really want is the error to go down. Now, in this case, we know what these two constants are, C1 and C2. C2 was just found to be what? 1 over the square root of 2. C1 was the reciprocal, turns out. So if you multiply the two together, you just get 1. Well, that's kind of nice because that tells us that that's a pretty small number. If this guy was astronomically large, then what I would have to do is adjust the number of smoothing steps that I do in order to make this whole number less than 1. If this number is large, then I have to use a lot of smoothings because remember the smoothing, so this constant looks like this. It's C1 over C2, sorry, C1 times C2 over M1 square root. So if this guy is, let's say, this guy is equal to 10. How many smoothings would we have to do? Well, this number here would have to be large enough so that the square, when I take the square root, I get a number which is less than 1. Well, okay, M1, if I take that to be 100, the square root of that is 10. So the product of this is 10 and this is 10. That's just going to give me a constant of 1. That's not going to work. I need a constant which is less than 1. So if this is 100, or sorry, did I say 10? Then I'm going to have to take M1 larger than 100. If I take M1 to be 101, everything works. If I take M1 to be 102, everything works. Any number, any integer number of smoothing steps, which is larger, strictly larger than 100, is going to give me or lead to convergence. And moreover, the important thing here is this convergence is completely H1 independent. So that's the key point. The convergence, H1 independent. That's the most important fact of all of this analysis. And the other important fact of this analysis is it was a heck of a lot faster and easier to do than the Fourier analysis in the Euclidean norm that we performed in chapter 3. So let's see how this works. How does it come together? Oh, I forgot to finish my thought. My thought was we know what this size of this constant is, right? It's just going to be equal to 1, right? So all we need to have is m1 such that the square root of m1 is going to be bigger than 1. Well, if I take it equal to 2, everything works because the square root of 2 is bigger than 1. So that number will give me something which is smaller than 1. So what should we do? Well, let's take m1 to be equal to 4, say. So then the square root of that is 2, and we get a contraction factor, an error reduction factor in the energy norm of what? It's going to be a half. 1 over the square root of 4, 1 over 2. So let's see how this works. All right, so the error transfer matrix for our two-grid method is precisely this. So this is something we showed in chapter 2. We used it again in chapter 3, and we're restating it here because we want to use this in our analysis. So this is the error transfer matrix, or just what we call the error matrix for the two-grid method. So remember what the two components are for the error. And it really represents what's happening in the algorithm. So in the algorithm, we're doing 2 steps. We're doing smoothing. Smoothing happens first, and that reduces the error in a certain way. And then second, we're applying a coarse grid correction, and that reduces the error in a certain way. So that's the two components of the error. And notice that they multiply each other. They're multiplicative. All right, so let's get into it then. E1L plus 1. So let's just be really explicit here. What do I mean? E1 L plus 1. That's the error, the true solution, what we sometimes call U1E, minus the iterate that we get after doing an application of the two-grid method one time, starting with U1L. All right. So, and of course, E1, let's just make it completely generic. So if I put in any number there, what do I want to use? Let's use S. In this case, S is going to be a positive integer. Okay, so this is now generic. Now that's any, so this is the error that at any stage in the two-grid algorithm. So now what we showed previously was that E1L plus 1 is equal to E1 times E1L. Okay, so that's what the error transfer matrix does, is it transfers the error from the L stage to L plus 1 stage. So this is an exact expression. Now, why are we computing the error in the energy norm? Well, let me just say something stupid. It's because what we're doing the analysis, or that's what we want to estimate. But the reason we're using the energy norm here is because the two properties that we use, the approximation property and the smoothing property, use that norm. So here's what I mean. What we're going to do first is we're going to apply the approximation property. Okay, so we're going to treat this piece here as just some arbitrary vector. Don't care what it is. So let's recall what the approximation property said. It said that if I apply this matrix times an arbitrary vector and I measure it in the A1 norm, then that's less than. So the estimate that I'm using is 6, less than a constant, times the square root of 1 over lambda 1, that's that, capital lambda 1, times that vector back measured in the A1 squared norm. Okay, so this is like the energy squared norm. So that's what the approximation property told us, that if you measure it, if you measure the size of this error, we can get this kind of reduction, and it's going to return this vector measured in this norm. So notice these two norms are not the same, but that's the best we could prove using the approximation property. Now, if you know a little bit about finite element method, so how many of you took finite element by electronically raising your hand? How many? One. I know there's more. How many of you took finite element method? A few of you. I know even more of you did. So this is related to the basic standard error estimate, energy norm error estimate of the finite element method. And I'm going to show you that when we get to chapter 6, how this is related. Remember how it went. Whenever we tried to get the error of the finite element method in the energy norm, what we produced was the true solution, okay, some constant times h, if we're using the piecewise linear finite elements, times u, the true solution measured in the H2 norm. Remember I said this is H2, or it's H2 light, the Sobolev H2 norm. That's where that comes from. And that's what I'm going to demonstrate for you in chapter 2. Right now, it's kind of mysterious, but that's where we're going and that's where it comes from. What else? Now, we want to apply the smoothing property. That was the approximation property. We want to apply the smoothing property. So that was pretty easy. Application of 6, no problem. It raised this error measured in the energy norm to something measured in the energy squared norm. But the smoothing property, notice that that was the smoother times an arbitrary vector measured in the energy squared norm. That's great because that's what we have. All right, so now we see the pieces of the puzzle fitting together. Now, what was that error? Okay, we just showed that that's C2 times the square root of lambda 1, capital lambda 1, divided by the square root of M1, times the error measured, or this vector measured in the energy norm. But we get some nice cancellation here, right? This guy cancels with that. Okay, see, that guy cancels. And all we're left with is C1 times C2 divided by the square root of M1 times the vector, or the norm, energy norm of the vector E1L. Well, if we can show that this is less than 1, then we have convergence. But we know that these are reciprocals of each other. That just gives us a 1. So as I said, this proves both the estimate and the result that I wanted to state, and that was if I take M1 large enough, and large enough here simply means that if M1 is greater than or equal to 2, then I'm going to get convergence in the energy norm, because this guy, this contraction factor, is strictly less than 1. Now, what can we show? What can we show by theory versus what can we show by experiments? Well, remember, let's go back to the theory that we learned in chapter 3. Remember, one smoothing iteration was enough to show convergence. And the contraction factor there in the one norm, the Euclidean norm, was about 0.9 something. Here, we can't prove convergence for M1 equal to 1. We don't get it because if M1 is equal to 1, this constant here turns out to be exactly 1. So the analysis is a little bit weaker because it doesn't show the convergence in the M1 case. So that is a slight failing of this analysis. But the analysis tools turn out to be much more powerful because they can be used in a broader landscape. The broader landscape is that they can be used whenever we're talking about these finite element methods on fairly complicated domains like I discussed last time. So we make a trade-off. We're trading precision of analysis with flexibility of analysis. So this type of error analysis can be used in a much more flexible landscape, and that's what we aim to do. All right, in the simplified setting, we showed that C1 is equal to C, the reciprocal of C2, and so that the product of the two constants just gives 1. So that means we know that if we have M1 greater than 2, greater than or equal to 2, then we have convergence. Now, or coming up in chapters 6, I think it is, chapter 6, where we do this for the general finite element method in 2 dimensions and 3 dimensions, etc. We can't know the exact values of these two numbers. However, we always know that those two numbers are going to be independent of M1, independent of H, independent of everything, more or less. The only thing they're going to depend on is the geometry of the problem that we're solving. Okay. Now, once the geometry is established, then all we have to know is that all we have to ask ourselves is, can we make M1 large enough so that this constant becomes less than 1 in size? And the answer is yes, because eventually some value of M1 is going to make this whole product be strictly less than 1, because this number is going down, right? It's getting smaller and smaller and smaller and smaller. And eventually the product of this two numbers which are fixed and this number which is getting smaller has to fit between 0 and 1 strictly. And once we do that, then we have our H1 independent rate of convergence. But as I said, that's coming later whenever we talk about the general finite element setting. All right, so we're back in chapter 5 now. Well, not back in chapter 5, but we're starting chapter 5 of Multigrid Methods, a mostly matrix-based course. But this chapter is actually called Multigrid because this is the first time we actually introduce these concepts. So this is part 1 of slide deck, slide deck 1 of 2 slide decks. Is that the right way to say it, I guess? So there'll be a second part that we'll cover in future lectures. But right now we're going to cover 3 sections of this chapter 5, namely the basics of multigrid, the building blocks of it. Then we're going to talk about the strong and weak approximation properties. Now, we talked about the approximation property in the last section, or the last chapter, chapter 4, and we only talked about one approximation property, and it turned out that that was what we called the strong approximation property. And then we're going to move on to the smoothing property, or the first smoothing property. Okay, so, and then more to come. Of course, we want to prove lots of types of convergences. Now, again, the reason why I call this a Moseley matrix-based approach is because the approach that you'll see here in chapter 5 and part 1 of chapter 5 in particular is that I'm not going to make any assumptions about where these problems are coming from, even though in the back of your mind you should always think, okay, Dr. Wise is obsessed with this problem. Minus Laplacian U equals F in some weird domain. Okay, something looked like a flying dragon with U equals 0 on the boundary. So this is the problem I'm trying to solve. And now, if you know anything about these problems, Calvin knows a lot about these problems because he's working with me to solve these types of problems right now. And some of my other students who are taking courses here are solving even more complicated problems. The PDEs are complicated, but the domain is maybe a square or something like that. But the whole theory that we're aiming at is getting fast solvers for the discrete version of this equation, which is going to be AU equals F. All right. So keep in the back of your mind that we're always trying to use the finite element method or maybe finite difference method to convert this problem, this more complicated problem, into this algebraic problem. Now, this is not just some algebraic problem, it's an algebraic problem which comes from this PDE. So it it doesn't live in this world all by itself, okay? It is attached to this problem and it has the structure, it inherits a lot of the structure of that problem. So this guy is just not some random problem that I'm trying to solve. It really has a lot of structure. For example, A is symmetric positive definite. And the other thing is I can really characterize its eigenvalues well. So that's what you should think about. I'm not necessarily going to be thinking about solving this problem on a fairly simple domain. I might be wanting to solve it on a complicated domain. But always in the back of your mind, keep in mind, we're really obsessed with trying to find solutions to this problem. Now, for those of you who aren't single-minded in your work, and that's probably 99.999% of you. You're not single-minded. You're always trying to solve different problems like AU equals F. They could be linear algebraic problems like this, but it's not always going to arise from this specific problem. However, like for example, some of the problems that my students are working on with the Cahn-Hilliard equation, you can still use these techniques to solve those problems. And so these techniques that I'm showing you are not simply associated to this one problem. They're widely applicable to many, many problems, as long as the structure is right. So it's not arbitrarily applicable, but it is widely applicable. That's what I want to impress upon you. All right, so the idea of multigrid, what is it? We had this two-grid algorithm, which is fairly simple to state. And it operated on two grids. What did we do there? What we did was we applied smoothing. Smoothing, we argued to ourselves, removed the high frequency components of the error. Then we computed a residual, and then we put that residual down on the coarse grid through a process known as restriction. When we were down in the coarse grid, then we solved a problem which was what we called an error equivalent equation, or an error type equation. Specifically, it looks something like this: A0 Q0 equals R0. Okay, so we solved this error equivalent equation, trying to argue to ourselves, well, if the error is missing its high frequency components, then hopefully the residual is as well. And then we solve this equation on the coarse grid, and then we send the results somehow back up to the fine grid. So that's the process. But this grid, this course level grid, might not be so simple, right? So for example, suppose it looks like that, right? So there's a level 0 grid and here's a level 1 grid. But now suppose that the fine level grid looks like this, getting finer and finer. Of course, this makes sense because this happens because we have to refine our mesh in a lot of cases to get the resolution of the answer that we want. So those of you in math biology, you might be saying to yourself, I don't really care about the numerical analysis side of it. What's the practical import? Well, if you're in math biology or mathematical physics, or you're doing some engineering type of problems, you're going to have to understand, and you probably already do understand, the importance of refining your mesh to get a better approximation result, refining your mesh to get a better or lower error. So sometimes you have to make a pretty fine mesh in order to get that small error that you want. Well, that would mean in our case that our fine level grid is pretty fine, and our coarse level grid is actually pretty fine as well. So this problem here becomes an issue to solve. Now, it might be only half of as expensive as the fine level problem, but it's still a problem in and of itself. So how do we solve that problem? Can we just multiply by the inverse? No. Um, if we could multiply by inverses, we wouldn't have to worry about solving this more complicated problem in the first place. We don't really have access to the inverse. So the idea of multigrid is to say, hey, you've got this two grid algorithm, but instead of solving this coarse grid problem exactly, just do what's called a recursive application of the two grid method. So you look at this problem and say, hey, I could apply the two grid method to that one. And then that creates a new coarse grid problem. And then you say to yourself, hey, I could apply the two grid method to that one. So it's like that picture of turtles all the way down, right? So you're stacking on top of turtles, they go all the way down. But there has to be a sort of coarsest course level turtle on which all the other turtles are standing. That's the kind of idea of multigrid. You do keep going down, but you get down to a grid where basically you can't refine it or you can't coarsen it anymore, and that's where you've reached the base level. So we're going to take our two grid algorithm and we're going to recursively apply it, and that's essentially what multigrid is. All right. Now this chapter developed out of my reading of a couple of really famous books, and they are the books by Brenner and Scott from 2008 and a book by Bress from 2007. So I didn't get this out of the ether. It's existed, the ideas and concepts here. And my presentation of it is a little bit different than those presentations. But I just want to say where things come from. Now, if you're really interested in multigrid, if you get and want to start digging in deeper into this stuff, then there's this book by Hackbush from 1985. Let's see, do I have a copy of it? I do. Actually, I have a copy of all three of these books. So the Brenner and Scott book is here, and it's called The Mathematical Theory of Finite Elements, and the oh, not that one yet. And the Bress book is just called Finite Elements. Maybe hard to see here. It's a Cambridge University Press book from 2007. Cambridge University Press is the press that published my book. And there are two books which those are finite element books strictly, and these books are on multigrid methods. The first one is a book by Westling, and it's called An Introduction to Multigrid Methods. So that's the green book. And then finally, this Hackbush book that I just mentioned is another book called Multigrid Methods and Applications. And it's in a newer copy or new printing, but it's actually from 1985. So a lot of these things are classical. So we want to go through the basic building blocks of multigrid. What are the basic building blocks of multigrid? Well, first we need a hierarchy of meshes. And now we're not going to assume that we have nested and uniform, or necessarily, we're not going to assume that we have uniform meshes anymore. We're going to get rid of that and use this sort of abstract approach, but it's an abstract matrix-based approach. Abstract matrix-based approach. So now all I have to think about is I have a hierarchy of spaces. And the hierarchy of spaces is like this. So I have at the top RNL. So that's simply vectors of length NL. And below that sits vectors of length NL minus 1. And below that sits vectors of arbitrary length L. And below that, dot, 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 we go down to the bottom, down to a smallest size vector space, Rn0. This is characterized by these numbers NL down to N0. And they have this hierarchical structure like this. NL is the biggest natural number, and N0 is the smallest, but it's still bigger than 1. All right, now what we're going to do is create a bunch of inner products on each one of these levels. And how should we create those inner products? Well, they're just the canonical inner products, and we call them level-dependent inner products. Now, they're all Euclidean inner products. And so remember, I decided from the very beginning not to call the Euclidean norm or the Euclidean inner product the 2 norm. That's because what does this mean? Does this mean P is equal to 2, or does it mean level is equal to 2? So I decided to say, okay, we'll always understand a norm or an inner product to be Euclidean, and the level number is going to indicate what it looks like. So the level L inner product takes 2 vectors, one from NL and the other from NL, and it puts them in its little slots, and it combines them together, turns the wheel, and gives you a real number out. That's what an inner product does. But of course, it has to have properties, right? It has the positivity property, symmetry property, et cetera, et cetera. Well, the Euclidean inner product already has all that stuff, and that's what we're going to use. ULVL on level L is just VL transpose times UL, okay, for any UL and VL in RNL. So remember, NL is just a number, and VL and UL are vectors of real components of length NL. And as before, we're always going to treat vectors that are arbitrary as being column vectors. So whenever I say column vector, that means if I need to combine 2 column vectors together, I'm going to combine them through matrix multiplication. And so if I'm to take 2 column vectors and multiply them together, what I have to do is transpose the first column vector, multiply it times the second vector, and I get a real number in the end. If I do it the reverse way, if I take VLUL, then that produces actually a matrix. But in any case, this should be familiar to you. Now, these are the components of these vectors. These are the canonical components of these vectors in the canonical basis. What is a canonical basis? So by that, I mean VL is equal to VL1, VL2, dot, 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 down to VL, NL. Okay. So that's what it looks like as a standard vector. But I could also write this in the canonical basis. Okay, so that's going to be sum k equals 1 to NL VLK. And then what I have to multiply this, I'm going to multiply it times the basis vector EK with respect to level L. Okay, so maybe I'll represent that like this, LK. Now this canonical basis vector is just the vector that has a 1 whenever I is equal, or sorry, K is equal to, so let's see. Yeah, so this one has a 1 in the kth position and a 0 everywhere else. It's the canonical one, right? So if I write those out in terms of components, then this works out to be that. So the standard Euclidean, I don't know why I'm wasting so much time on it. It's just the standard Euclidean inner product. Now I need the following little property, and this is a cute little property, and one that I could have stated earlier, but didn't, but it holds true. Suppose that NL and NL minus 1 are not the same numbers. Of course, they're not allowed to be, okay? NL is bigger than NL minus 1, as it should be, according to this hierarchy. And suppose that B is a matrix that is not square. It has NL minus 1 rows and NL columns. See, it has a few less rows than columns. Now, you might think that it has one fewer row than it has columns. That's not necessarily true. It depends on the size of these two numbers. So, for example, this number here could be 6 and this number could be 3. So it might have 3 rows and, what did I say, 6 columns. Then for any UL in RNL and any VL minus 1 in RNL minus 1. So this subscripts here are supposed to be evocative of the fact that this guy is coming from level L. And this subscript means that this vector is coming from level L minus 1. Okay? So now B times UL. So first of all, let's think about this to ourselves. This has to be compatible for matrix vector multiplication. So let's look at it like this. I have a B times a UL. Does that thing make sense, and where the heck does that live? Well, this matrix B has NL minus 1 rows and NL columns. And this is a column vector, and it has NL rows and 1 column, right? Column vector. So that means it's the product of this thing, and the product I can call something like W, and I'm going to foreshadow the answer here, WL minus 1. What's the size of that guy? Well, it's going to be NL minus 1 by 1, which in other words means that that's a vector in RNL minus 1. Now, I'm going to bypass this a lot of times and just say the product here is a level L minus 1 vector. See how I'm saving a lot of writing and words by saying this is a level L minus 1 vector rather than this is a vector from R and L minus 1. And in other words, when I multiply B times UL, I get a vector which has NL minus 1 components. So it's in R and L minus 1 or in level L minus 1. So I can take its dot product, Euclidean dot product, or Euclidean inner product with another vector on the same level. So that inner product, of course, I'm going to use the L minus 1 inner product. Why not? Well, this matrix moves over essentially to the other side, but when it does so, it gains a transpose. But keep in mind, this isn't an ordinary transpose because B is not a square matrix. Now B, because it's non-square, whenever I take the transpose, the number of columns and the number of rows flip. So now what is B transpose? B transpose is a matrix with NL rows and NL minus 1 columns. I can multiply that times a vector in Rn L minus 1 or a level L minus 1 vector. It's much harder to say than it is to write. And this whole thing gives me a vector of length NL, or in other words, a vector in RNL. Well, I can take its Euclidean inner product with this object, UL, right? Euclidean inner product on level L, and all of it makes sense. So everything here makes sense. But the fact that they're equal is the punchline of the result. When I throw this guy over to the other side, I have to change one thing, or two things. I have to change the matrix to its transpose, and I have to ratchet down or I have to ratchet up the level of the inner product. So maybe I would better call this the ratchet proposition. Okay, so whenever I take a transpose, I have to change the B to B transpose, of course, throw that to the other side, and this guy gets ratcheted up. And the proof is just left as an exercise. It's fairly simple. Now we're going to assume basic properties like we've seen before, but now everything is completely abstract. We're not referring to a grid, and the grid is certainly not necessarily uniform. We're going to assume throughout this chapter and everywhere else, unless we specify otherwise, that RL minus 1 is going to be a matrix which is non-square, and it looks like that matrix B that we had in the last slide. It has NL minus 1 rows and L columns. And we're going to assume that each one of those restriction matrices is full rank. Okay, and why not? Let's call it a restriction matrix. Not sure why I didn't say that. So this guy is the restriction. Okay, and it's full rank. Well, its full rank must be the lesser of these two numbers. And the lesser of the two numbers, of course, is NL minus 1. And what else should we do? Well, makes sense. Let's let the prolongation be equal to the transpose of the restriction operator. So this guy here is the prolongation. As usual. And now, based on that little result that I had in the last slide, whenever this matrix comes over to the other side, it gains a transpose. So if I start with the restriction matrix over here, remember a restriction matrix takes a vector in the fine level and maps it down to the coarse level. Now, the coarse level in this case is what we're going to call a relatively coarse level or a relative coarse level. And that's relative to L, the coarse level for L is L minus 1. So it's going to move a vector on level L to level L minus 1. So that's exactly what the application of the restriction matrix does. So this makes sense, right? But now if I want to move this guy over to the other side, it's going to gain a transpose, but its transpose is just going to be PL minus 1 according to this prescription. By the way, that means that PL minus 1 also must be a full rank. Now, remember, now we're going to use our ratchet, and that's going to change the level of this inner product from L minus 1 to L, so it gets ratcheted up. Now, we're also going to assume, as part of our basic building blocks of multigrid, is that we've got this family of SPD stiffness matrices. And why are they called stiffness matrices? Well, it's because the matrix A in this relation, whenever this arises from a finite element method, well, this guy here, A1, is called a stiffness matrix. So that's why I'm going to look at a family of stiffness matrices, because now when I do my recursive 2-grid, I'm going to produce this thing called multigrid, and I need to have some concept of my stiffness matrix on every possible level. So I need to have a family of stiffness matrices AL from L equals 0 to L equals capital L. Capital L is going to represent for us our finest possible mesh. Okay, the finest possible mesh. So these stiffness matrices get larger and larger. So they're always going to be square. They're always going to be positive definite, but they just start ballooning up, etc. Right? They get bigger and bigger. They're always SPD. Maybe the eigenvalues are related to each other, maybe not. We'll get into that momentarily. But no matter how these things are defined and where they come from, we're going to define energy inner products in the usual way. We define the energy inner products through the Euclidean inner product. So the AL energy inner product on level L for an arbitrary vector UL and arbitrary vectors UL and VL is just defined as AL UL against VL in the level L Euclidean inner product. And I should have said here for any UL VL in RNL. Okay. And now our goal is to solve, what would our goal be? Our goal would be to solve the problem on the finest possible level. The finest possible level is the level L equals capital L, finest possible. And the level L equals 0, well, that's the coarsest. So what have we seen previously? So we've only seen previously L equals 1 and L equals 0. So the finest possible level was the level L equals 1, and the coarsest level was equal to 0, L equals 0. I have a question in chat. Okay. So the question is when I write it, is it going to be NL minus 1, where the minus is subtracted from NL, or is it NL minus 1, where both the L and the minus 1 are in the subscript? It's the latter. The L and the minus 1 are both in the subscript. Okay, so in all of these things, whenever they're written out, the L minus 1 are both in the subscript. It's not NL minus 1. So this is not the same as saying, see if I can make it look like. That's not NL minus 1. In some cases it is, but in the most general and abstract case that we want to study, it is not. Both of those numbers appear in the subscript, or all of the things appear in the subscript. All right, so the problem that we want to solve is that problem on the finest level, ALUL equals FL. And I'm going to kind of bias the finest level a little bit. And I'm going to say the true solution in there on that finest level, I could just call that UL without any dress ups. But I'm going to dress it up and give it E to represent the exact solution. That dress up is not required, but it's kind of helpful sometimes to keep track of it. So what is given to us? What is given is AL, and that is going to be part of our family of stiffness matrices. And FL is going to be a given forcing vector. And now the names and nomenclatures are sort of historically related. Stiffness refers to the stiffness of a spring system. U is the usual letter for displacement in the mechanics literature. And F is for force, and that means force. So this is like a spring type equation, or a generalized, or at least the nomenclature reflects that it's a generalized elasticity equation. Stiffness matrix times the displacement vector equals the forcing vector, or the forcing load. All right, so the forcing vector is what's given, and the displacement is what must be determined in this whole problem setting. Now, as usual, I wanted to find the error, no matter what the process is or where we are in the process. If we're measuring the true error, then that's the only thing that's getting this label E. Now, if I have a canonical vector, and I think I broke my promise or rule earlier. No, I did. I didn't. So when I have a canonical basis vector, that also is usually listed by an E, but it gets a hat put on it. If we're talking about the error vector, that also has an E, but it's usually with an arrow above it, or just boldface. Again, if it's a basis vector, it looks like, and it's impossible for me to distinguish or show you something which distinguishes between boldface and non-boldface. So I just mean boldface gets an arrow, right? And so that would mean that my canonical basis vectors would look like that if I'm writing them on the page. And I guess, yeah, I should have put that little arrow symbol there. Okay. But the only thing that I want you to think of, unless I say otherwise, when you see E, is think error. And that's always measured from the true solution, ULE. Okay. There's no such thing as an error on level capital L minus 2. It doesn't make any sense. The error makes sense only on the finest level. So that's why we're using capital level, or capital L there. Similarly, we define the residual always as RL is FL minus ALUL. And so that satisfies an error equation. So this is sometimes called the residual error equation. And it always satisfies the same thing. ALEL equals RL. All right, so now I think, yeah, I'm going to try to steamroll through this and take maybe an extra minute. So I'm going to now define the multigrid operator. So the multigrid operator is going to be defined in a couple of steps. I'm not going to go into all of the details of it. I'm simply going to give it a broad overview, and then we'll come back and hit it with a very fine level examination next time. So suppose that L is somewhere between the coarsest possible and the finest possible, and GL is some arbitrary vector from level L. This guy should be, that's missing here, that should be UL 0. And that is an initial guess on level L. So these guys are all given. Then the vector UL3 in parentheses is computed via the recursive multigrid operator, and the recursive multigrid operator is defined here in the following steps. Here we go. If the level is equal to the coarsest possible level, then what I'm going to do is I'm simply going to apply A0 inverse. So on the coarsest possible level, I'm going to exactly solve the problem via A inverse at the 0 level times G0. And that's what I'm going to set to U03. Okay, so it's very easy to define what I'm going to do on the coarsest possible level. Now, if it's not on the coarsest possible level, here's what I'm going to do. Okay, and then we'll come back to this later. If it's not on the coarsest possible level, I'm going to do two things, or actually three things. I'm going to do pre-smoothing. I'm going to smooth it. So if it's not on the coarsest possible level, I'm going to take that G operator and I'm going to use that in a smoothing process with the error transfer matrix for smoothing, or not, actually, this is called the iterator matrix for the smoothing, SL. And I'm going to apply a loop which does M1 applications of this general linear iterative scheme. And that's what I'm going to call my pre-smoothing step. Next, once I get that pre-smooth step, I'm going to call that UL1, by the way. I'm going to compute a residual for that. I'm going to push that residual down to the coarse grid, the relative coarse grid, using the restriction operator or restriction matrix that I have associated, right? Then I'm going to somehow, and this is where the magic happens, so just write the word in your notes, magic happens. I'm going to somehow compute what's called a coarse grid correction, and this is where the multigrid magic happens. I'm going to add that back to the last best guess I had for that, and that last best guess was this guy gotten through smoothing, and I'm going to call that UL2. And then I'm going to follow that all up with doing a post-smoothing step. And the post-smoothing step is I'm going to use, instead of using the iterator matrix SL, I'm going to use SL transpose. Okay, I'm going to use this as my initial guess. And I'm going to do M2 applications of this general linear iterative scheme. And I'm going to call that the post-smoother or the post-smoothing step. And you can see what you end up with in the end is something 3M2. That's what I'm going to call my output vector UL3. All right, so you see how it goes through, starting with some initial guess. It's going to go through three stages. As long as you're not at the coarsest level, you do pre-smoothing, a coarse grid correction, magic happens here, add that coarse grid correction, then finally smooth. And that is the multigrid operator. I'm going to stop there. And thank you for those extra 3 minutes. I apologize for going over. I'll take any questions you have right now. And thank you.